Okay, Chapter 17, Problem 51. Here we're told that the electric field between the plates of a paper-separated capacitor is 8.24 times 10 to the 4 volts per meter. The plates are 1.95 millimeters apart, and the charge on each is 0.675 microcoulombs. We are asked to determine the capacitance of this capacitor and the area of each plate. So let's go ahead and have a picture going on here. So here are the two parallel plates of this capacitor. Let's imagine this side has a whole bunch of plus charges, and on this side a whole bunch of minus. Okay, there's going to be some separation, D, which they give us the number for. In between, there's paper in between, which has a particular dielectric constant, which I'll call K, capital K. And let's go ahead and write down the things that they want. We want to figure out what is the capacitance, so capacitance C, and the area of each plate A. Okay. They tell us the dielectric constant for paper, 3.75, the electric field magnitude is 8.24 times 10 to the 4 volts per meter, and the charge on each plate, Q, so here's a plus Q and here's a minus Q, that charge is 0.675 microcoulombs, or 10 to the minus 6 coulombs. Okay, and we're supposed to figure out the capacitance and figure out the area. They're telling us some things that are perhaps useful. First of all, let's see if we can remember what is the definition for capacitance. So capacitance is defined as the amount of charge stored on the capacitor divided by the voltage applied to the capacitor. Okay, or if you like, V here is also known as delta V, but it's simply the difference in potential between one side and the other. I'm going to go ahead and box that because I think we're going to need it. Something that we should have seen in class is that the capacitance for a parallel plate capacitor involves, remember, the capacitance is bigger the larger the surface area is. It's bigger when the plates are closer. There's a constant that tells us how the capacitance relates to A and D, and if there's a dielectric in between, then the capacitance grows in proportion to that dielectric constant K. So that's relevant. It's also a bit of a hint that they're telling us the magnitude of the electric field, and how might that enter into this discussion. There's actually a hint here also in the fact that the units are volts per meter. Recall that the electric field can be related to the change in potential divided by the separation, delta x. Okay, so for us in this particular problem, I'm going to go ahead and point out that the potential from one place to another, that potential difference, delta V, I'm just using the notation V, and the separation from one place to another, that's going to be D. So that allows us to relate the electric field to the voltage and the distance, and that may be necessary in a moment. And let's go ahead and leave it there. So the first thing to do is to see if we can figure out what is the capacitance. Well, the capacitance relates to the charge and the voltage. They give us the charge, they don't give us the voltage. And so that was actually kind of the hint to start thinking about what can we use to figure out the voltage. Well, remember, the voltage relates to the electric field and the separation. So let's go ahead and use this to write the electric field times the separation. That should be the voltage. So in fact, the capacitance can be written as Q divided by electric field times D. When you stick in all those numbers, you'll find that this is roughly 4.20 times 10 to the minus 9. And if you think about what the units are going to be, on the top, coulombs, on the bottom, volts. So I can write that as a coulomb per volt, but as you perhaps remember, that the units for capacitance also takes the form of farad. So this is, if you like, farad. 10 to the minus 9 is the same thing as nano, so I can write this as 4.20 nanofarads. That is the capacitance of this parallel plate capacitor. The last thing to do is figure out what is the area of any one of these plates. The only formula that the area comes in is right here. in this equation. So let's see if we can determine what the area is. Apparently, if we solve for the area, the capacitance times D divided by K epsilon naught, that should do it. We've already computed our capacitance of the 4.20 times 10 to the minus 9 farad, the separation, which I have not written down. I should have done that before, excuse me. D is 1.95 millimeters, or 1.95 times 10 to the minus 3 meters. 1.95 times 10 to the minus 3. Dividing this by K, 3.75, and epsilon naught, which is that tiny 8.85 times 10 to the minus 12, with the units of coulombs squared over newtons times meters squared. This should be the area. When all is said and done, this turns out to be about 0.247 meters squared for your final answer for here.